Welcome to our exploration of kinetics of particles, a fundamental branch of engineering mechanics that delves into the fascinating world of motion and forces. Kinetics is more than just a scientific term. It's a powerful analytical approach that bridges the gap between forces and motion. At its core, kinetics deals with the dynamic relationship between forces acting on a particle and the resulting movement. Imagine it as a detective story where forces are the suspects and motion is the crime scene we're trying to understand. By developing mathematical models, kinetics allows engineers to predict and explain how particles move under various force conditions. Whether it's a projectile launched from a cannon, a car accelerating on a road, or a satellite orbiting the Earth, kinetics provides the tools to comprehend and analyze these complex motions with precision and clarity. Let's delve into the concept of the equation of motion. The motion of a particle is governed by Newton's second law. This law states that the net force acting on a particle is equal to the mass of the particle multiplied by its acceleration. In simpler terms, this means that the force exerted on an object will cause it to accelerate, and the amount of acceleration depends on the object's mass. For example, if you push a small toy car and a real car with the same amount of force, the toy car will accelerate much more because it has less mass. This fundamental principle helps us understand how forces cause changes in the motion of objects and is essential for analyzing the dynamics of systems in physics and engineering. Let's look into the general form of force and motion in 3 dimensions. In 3-dimensional space, the motion of a particle can be described by resolving the forces and accelerations into their respective components along the x, y, and z-axis. Newton's second law of motion applies here as well, stating that the net force acting on a particle is equal to its mass multiplied by its acceleration. This can be expressed in 3 dimensions as follows. The force component along the x-axis is equal to the mass of the particle multiplied by its acceleration along the x-axis. Similarly, the force component along the y-axis is equal to the mass of the particle multiplied by its acceleration along the y-axis. Finally, the force component along the z-axis is equal to the mass of the particle multiplied by its acceleration along the z-axis. These components help us understand how the particle moves in 3-dimensional space, providing a comprehensive view of its motion and the forces acting upon it. Equation of motion. This powerful tool is not just a theoretical concept, but a practical approach used across numerous engineering disciplines. Consider how it's applied in calculating the motion of projectiles. Engineers can precisely predict the path of a missile or understand the trajectory of a sports ball. In automotive design, these equations help engineers optimize vehicle performance, design safer braking systems, and understand how vehicles respond to different forces. From understanding the dynamics of vehicles to analyzing complex mechanical systems, the equation of motion provides a critical framework for solving intricate engineering challenges. It's the mathematical bridge that connects theoretical understanding to practical application, enabling us to predict, design, and improve mechanical systems with unprecedented accuracy. Rectilinear motion is the simplest form of particle movement, occurring in a straight line. It can be understood through 3 key parameters: position, velocity, and acceleration. Position indicates where the particle is, velocity tells how fast it's moving and in what direction, and acceleration describes how quickly its speed changes. By analyzing these components, engineers can predict an object's movement with precision. The kinematic equations for constant acceleration describe how an object moves under steady acceleration. These equations help predict the relationships between position, velocity, time, and acceleration, enabling accurate analysis of straight-line motion. This knowledge is essential in fields like transportation design, physics, and engineering problem-solving. While constant acceleration provides a straightforward model of motion, real-world scenarios often involve more complex, non-uniform acceleration. Picture a roller coaster climbing a steep hill, or a car navigating through city traffic. These are scenarios where acceleration is constantly changing. Non-uniform acceleration introduces a layer of complexity that requires more sophisticated mathematical approaches. Engineers must account for varying forces, changing velocities, and dynamic environmental conditions. This type of analysis becomes crucial in fields like automotive design, aerospace engineering, and robotics, where motion is rarely as simple as a steady, unchanging acceleration. By developing advanced mathematical models, we can capture the nuanced and dynamic nature of real-world motion, providing insights that go far beyond simple linear movement. Curvilinear motion involves particles traveling along curved paths in 2- or 3-dimensional spaces, requiring sophisticated mathematical analysis. Examples include a car turning on a winding mountain road, a planet orbiting the sun, or a gymnast performing an aerial maneuver. Engineers use coordinate systems like rectangular, normal tangential, or cylindrical to describe and predict these motions. Projectile motion, where a projectile's path forms a parabolic curve, and the circular path of a car navigating a curved road, illustrate curvilinear motion's complexity. This motion is fundamental in everyday life and engineering, from spacecraft trajectories to athlete movements and celestial orbits. In curvilinear motion, acceleration becomes a complex interplay of two distinct components that reveal the intricate nature of particle movement. The first component is tangential acceleration, which changes the speed of the particle along its path. The second is normal, or radial, acceleration, which alters the particle's direction without changing its speed. Think of a roller coaster rounding a bend. The tangential acceleration might increase or decrease the coaster's speed, while the normal acceleration causes it to change direction. This dual nature of acceleration in curvilinear motion provides engineers and scientists with a powerful tool for understanding and predicting complex movements. By breaking down acceleration into these components, we can precisely analyze how forces influence the motion of particles in curved paths, opening up incredible insights into mechanical and physical systems. The work-energy principle is a significant breakthrough in understanding mechanical systems. It serves as a bridge connecting the work done by forces to changes in a particle's kinetic energy. This principle simplifies complex dynamics problems by focusing on energy transformations rather than tracking every individual force and acceleration. Engineers can analyze the work done on a particle and directly understand how its energy changes, making it easier to solve complex problems. By emphasizing energy transformations, this principle offers deeper insights into mechanical systems beyond traditional force-based analysis. Work is not just a casual term, but a precise scientific concept that quantifies the energy transfer when a force moves an object. Picture a person pushing a heavy box across a floor. The work done depends not just on the force applied, but on the distance the box moves and the angle between the force and displacement. When the force and displacement are in the same direction, maximum work is done. When they're perpendicular, no work occurs. This nuanced understanding reveals that work is more than simple pushing or pulling. It's a calculated measure of energy transformation. Engineers and physicists use this concept to analyze everything from machine efficiency to the energy expenditure in biological systems. By breaking down work into its fundamental components, we can precisely quantify how forces create movement and energy changes in mechanical and natural systems. Kinetic energy is the energy an object has because it's moving. It increases significantly with speed, so a faster object has much more kinetic energy. For example, a baseball thrown at 100 miles per hour has much more kinetic energy than one thrown at 50 miles per hour. This helps engineers and scientists predict how moving objects will interact, which is crucial for things like designing safer vehicles and understanding planetary motion. Work energy principle states that the total work done on a particle is equal to the change in its kinetic energy. It's like an energy balance sheet showing how forces change an object's energy. By focusing on energy changes instead of individual forces, engineers can solve complex problems more easily, such as analyzing roller coasters, rocket trajectories, or machine performances. This principle is used across many engineering fields. For instance, in crane operations, engineers calculate the required energy to lift materials. Roller coaster designers use it to ensure safety and excitement. In automotive engineering, it helps create efficient braking systems and improves vehicle performance. Even in biomechanics and robotics, it provides insights into motion and energy transfer, making it a universal tool for designing and optimizing complex systems. The law of conservation of energy states that energy cannot be created or destroyed, only transformed. This means that the total energy in a system, combining kinetic and potential energies, remains constant. This principle shows how energy transitions smoothly between different states, like in pendulum swings and planetary orbits. Mechanical energy conservation is the process of energy transforming between potential and kinetic forms. For instance, a roller coaster at its highest point has potential energy, which converts to kinetic energy as it descends. In the absence of friction, the total mechanical energy remains constant, explaining the seamless transformation of energy in systems from pendulums to planets. Engineers and physicists use this principle to analyze and predict mechanical systems, showcasing energy's consistent integrity. In the mathematical form, the conservation of energy is expressed as follows: the total energy at one point, which combines kinetic energy and potential energy, is equal to the total energy at another point. This is represented by the equation. The energy at one point, labeled as point 1, equals the energy at another point, labeled as point 2. When non-conservative forces, such as friction, are present, the work done by these forces alters the total mechanical energy. This is represented by the equation. The energy at point 1 plus the work done by non-conservative forces equals the energy at point 2. For instance, in a pendulum, energy shifts between potential at its highest point and kinetic at its lowest point. Similarly, in a roller coaster, energy constantly transforms between potential and kinetic as it moves through peaks and valleys. When forces like friction are present, they do work that alters the total mechanical energy. By understanding these principles, we can analyze and predict the behavior of various mechanical systems. Let's explore the concept of impulse and momentum. Momentum is the quantity of motion an object possesses. It's calculated by multiplying the mass of the object by its velocity. Since momentum is a vector quantity, it has both magnitude and direction. For instance, a moving car has momentum proportional to its mass and speed, and its direction corresponds to the direction of travel. Impulse, represented by the symbol J, refers to the change in momentum of an object resulting from a force applied over a period. It's calculated by multiplying the applied force by the duration of its application. The impulse momentum theorem states that impulse equals the change in momentum, showing how a force changes an object's motion. In mathematical terms, This is expressed as the impulse J being equal to the mass of the object times the difference in its final and initial velocities. Essentially, impulse measures how much a force alters the motion of an object. Let's discuss key observations about impulse. A large force applied for a short duration can produce the same impulse as a smaller force applied over a longer duration. For example, in sports, hitting a cricket ball or a baseball involves applying a large impulse to change its momentum quickly. In car collisions, airbags increase the time of impact, reducing the force experienced by passengers, thus illustrating the principle of impulse effectively. Let's discuss the conservation of momentum. This principle states that in the absence of external forces, the total momentum of a system remains constant. Essentially, momentum is conserved before and after any interaction within the system. For example, in a collision between two objects, the total momentum of the objects before the collision equals the total momentum after the collision. This principle is represented mathematically by summing the initial and final momenta, showing their equality. Understanding this law helps analyze and predict outcomes in various scenarios, such as vehicle crashes, explosions, and even in sports, where interactions between players and equipment follow the same rules. Continuing with the concept of conservation of momentum, let's discuss the types of collisions. There are two primary types, elastic and inelastic collisions. In elastic collisions, both momentum and kinetic energy are conserved. This means that the total momentum and total kinetic energy before and after the collision remain the same. For instance, if two balls collide, the sum of their momenta and kinetic energies before the collision is equal to the sum after the collision. In inelastic collisions, only momentum is conserved, while kinetic energy is not. This means that although the total momentum remains constant, some kinetic energy is converted into other forms of energy, like heat or sound. An example is when two cars collide and stick together, they move with a common velocity after the collision, with some energy lost as heat or sound. Understanding these types of collisions helps us analyze and predict the outcomes of interactions in various scenarios, from car crashes to sports and even astronomical events. Let's talk about the conservation of momentum in explosions. When a system is initially at rest, the total momentum remains zero. During an explosion, the fragments move with momenta that are equal in magnitude but opposite in direction. For example, in rocket propulsion, gases expelled backward exert an equal and opposite force, propelling the rocket forward. Similarly, when a gun is fired, the momentum of the bullet is balanced by the recoil momentum of the gun, demonstrating the conservation of momentum. The principles of momentum and impulse find applications across numerous engineering disciplines, demonstrating their fundamental importance. In automotive design, understanding momentum helps create sophisticated safety features like crumple zones that dissipate impact energy. Aerospace engineers use these principles to design precise spacecraft docking procedures and analyze complex propulsion systems. Machine tool design relies on momentum principles to optimize cutting and forming processes. From robotics to sports equipment design, from industrial machinery to transportation systems, momentum conservation provides a universal framework for understanding and predicting motion. It transforms our approach from simple force measurements to a comprehensive analysis of how objects interact and move. Let's discuss the impact of bodies. When two or more bodies collide within a very short time, it's called an impact. During this event, high forces act over a short duration, causing possible deformation, which can be either elastic or inelastic. We use momentum and energy conservation principles to analyze motion before and after impact. Impacts are categorized into two types. Central impact occurs when the line of impact passes through the centers of mass of the colliding bodies. Oblique impact happens when the line of impact does not pass through the centers of mass, resulting in tangential velocity components. The impact process has two phases. Deformation phase. The bodies deform, storing energy. Restitution phase. The bodies recover, partially or fully, releasing stored energy. Let's discuss the coefficient of restitution, a key concept in understanding collisions. The coefficient of restitution, denoted by the symbol E, quantifies how elastic a collision is. It's the ratio of the relative velocity of separation to the relative velocity of approach. In simple terms, it measures how bouncy a collision is. For instance, if two objects collide, the coefficient of restitution tells us how much of their initial speed is retained after the collision. Mathematically, the coefficient of restitution is calculated as the difference in final velocities of the two bodies divided by the difference in their initial velocities. This dimensionless value ranges from 0 to 1, where 1 indicates a perfectly elastic collision with no kinetic energy lost, and 0 represents a perfectly inelastic collision where the objects stick together. Understanding this concept helps in analyzing and predicting the outcomes of various collisions. Understanding the coefficient of restitution, denoted as E, helps categorize collisions. Perfectly elastic collision, E equals 1, no energy is lost during impact, like gas molecules colliding. Partially elastic collision, 0, E less than 1, some energy is lost as heat, sound, or deformation, such as a ball bouncing on the floor. Perfectly inelastic collision, E equals 0, the bodies stick together after impact, resulting in maximum kinetic energy loss, like two clay lumps sticking together. These categories help analyze the nature and energy transformations in collisions. Let's discuss the loss of energy during impacts. In real-world collisions, some kinetic energy is always lost due to the deformation of materials, heat generation, or sound production. This can be evaluated using the formula for the loss of energy, which is the initial kinetic energy minus the final kinetic energy. In perfectly elastic collisions, no energy is lost, meaning the initial and final kinetic energies are equal. Let's talk about the loss of energy during an impact. In partially or perfectly inelastic collisions, the initial kinetic energy is greater than the final kinetic energy. The energy lost is dissipated as heat, sound, and permanent deformation. This means some of the energy that was originally in motion is transformed into other forms, demonstrating the conservation of energy in real-world scenarios. Let's discuss the loss of energy during an impact. The energy loss can be calculated using a specific formula that incorporates the masses of the colliding bodies and their velocities. The formula is delta Ke equals 1/2 times the product of the masses divided by the sum of the masses, multiplied by the square of the relative velocity of approach minus the square of the coefficient of restitution times the relative velocity of approach. This calculation helps us understand how much kinetic energy is lost and transformed into other forms like heat, sound, or deformation during collisions. Impact analysis has vital engineering applications across various fields. In sports, engineers optimize equipment such as bats and helmets to enhance performance and safety. In crash testing, vehicles are designed to protect passengers during collisions. Material testing assesses resilience, helping choose the best materials for construction and manufacturing. In industrial machines, impact analysis ensures the efficiency and durability of equipment like hammers and pile drivers. These applications highlight the importance of impact analysis in designing safer, more efficient, and resilient products across engineering disciplines. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.